Hello everyone, welcome to the series of lectures on the course Foundations of Mathematics. This is part 2 of the first chapter, Sets, and the title is Operations on Sets. Let's see what are the operations on sets. Okay, now if you consider the set of natural numbers and we have operations on the set of natural numbers like addition, subtraction, multiplication, and division, right? And what does that give is if you start with some numbers and if you apply these operations to those numbers, you are going to get more numbers from these operations, right? So in a similar way, we have operations on sets, and when I use these operations on sets, it creates more sets. Okay, so let's see what are the operations on sets. The first one is called the union of sets. So if I have two sets A and B with me, so let A and B be two sets, then the union of A and B is defined as the set of all the elements which are there either in A or in B. Okay, and it is denoted by this A union B. So this notation is for union, and A union B is collection of all those elements which are either in A or B. Now when I say either in A or B, what does it mean? It should be in at least one of A and B. It can be in both also. Okay, so all such elements will be coming in the union of these two sets A and B. All right. Now that is same as saying a point X will come in A union B if and only if it's a definition, the union of two sets, that's a definition. And we have seen that definitions are nothing but if and only if statements. So I can also restate this as X belongs to A union B if and only if X belongs to A or X belongs to B. Okay, so this is just another way of writing it. So this is union of two sets. The second operation on sets is intersection of two sets. So the intersection of the sets A and B is a set defined by this. What I'll do now? I will collect all those elements which are there in both A as well as B. Fine. So the set of all X such that X belongs to A and X belongs to B. This set is called intersection of these two sets. Intersection meaning the common elements which are there in both A as well as B. And it is denoted by this notation. A intersection B, it is read as A intersection B. This notation is for intersection and it is defined as this set. Okay. So again, this is a definition. So it's an if and only if condition, and I can also state it as X belongs to A intersection B if and only if X belongs to A and X belongs to B. Okay, so these are two operations on set. One is union and one is intersection. So let's look at some examples. Look at these two sets. The set capital A is defined to be set of all ordered pairs xy in R2 in your xy plane such that x square plus y square equal to 1. Okay, and B is set of all ordered pairs xy in R2 such that x is equal to 1. So can you all identify this set A? What is this set A? Collection of all ordered pairs which satisfy this equation, and this is the equation of unit circle around the origin, right? And if you look at the other set B, that is collection of all ordered pairs xy such that the first coordinate x is 1. So this is nothing but the line passing through the point 1 on the x-axis, which is parallel to the y-axis, right? Now what I want to do is I want to find out which are the elements in A intersection B. I want to find the intersection of these two sets. Okay, and best way to look at this would be to see their graphs. All right, So I will show you the graph of these two sets in the xy plane. Okay. Here is the xy plane, and I've plotted the set A, okay, which is nothing but the unit circle around the origin, as you can see here, and the line x equal to 1 is this, which is your set B. Okay, x equal to 1. And from here it's quite clear that only one point is there which is common to both the graphs, and that is this x equal to 1, or you can say 1 comma 0 in the xy plane, right? So this is the only point which is common to both the sets A and B. So what will be the intersection? Their intersection will contain only one point, that is 1 comma 0, which is this point which you can see here where my cursor is. Okay, so looking at sets graphically, it gives you a better idea of what will be their intersection or union. Okay, so let me go back to the problem. It's quite clear that intersection of these two sets is only one point, that is 1 comma 0, but we'll have to prove it. Okay, so what we'll do, we'll take one point in the intersection and we will show that only possibility is that it is 1 comma 0. Okay, so let me start with the point. I'll take a ordered pair, let's say p comma q, say, belong to A intersection B. Now p comma q, this ordered pair is there in A intersection B. This means that ordered pair pq is there in A and it is there in B as well. Okay, so it is there in both these sets. Now because it is in A, it will satisfy this equation p square plus q square equal to 1. So let me put that. So this implies p square plus q square is equal to 1. And from here, because this ordered pair is in B, and the only condition on points of B is the first element has to be 1, and that's that element here is P. That means P is equal to 1. So I have got two conditions now. So P equal to 1, this value I'll take and I will drop it here in this equation, and that will give me 1 plus q square is equal to 1. Okay, and this further says q square is equal to 0, which means q is equal to 0. So I have obtained the values for p and q. Okay, so this p comma q is nothing but A intersection B. So if you take any point p comma q in A intersection B, it will be 1 comma 0. It has no other choice. Okay, so the set A intersection B is a subset of this singleton set having this ordered pair 1 comma 0. Right, so I'll name this as something, let's say star, and now I'll take the point from this set. There is only one point, and that satisfies both the conditions, the condition in A as well as B, right? So I will take 1 comma 0 and I will say that it satisfies both the conditions. Also 1 comma 0 is there in A and 1 comma 0 is there in B also. So this implies 1 comma 0 is there in their intersection. That means every element from this set is there in the intersection. That means that set having one element 1 comma 0, this ordered pair is also a subset of A intersection B. And I'll name this double star. So from star and double star, what is the conclusion? We conclude that A intersection B is nothing but the singleton set having the element 1 comma 0. Okay, so this is the intersection of these two sets. I hope that's clear. So moving on to the next two examples, I will leave these two examples for you all. Okay, so you all try to find the intersection and the union wherever it is asked. The second one says, let A be the set of integers which are divisible by 2 and B be the set of integers which are divisible by 3. Then you are asked to compute their intersection. Okay, so do try this, a very simple one. And the third one, A is the set of all real numbers whose square is greater than or equal to 0, and B is the set of all real numbers whose cubes is greater than or equal to 0. And you are told to find the union as well as the intersection. Okay, so I expect you all to solve these two problems. Okay, next, associative property, associativity. If I have three sets A, B, and C with me, then the union and the intersection, these two operations, they satisfy the associative property. Now, what does that mean? I have three sets A, B, C. What I do is I take union of B and C first. So I get this term B union C. So finally, I have one set with me. So I will take union of A along with this set, right? So I'm taking union of B and C first, and then I'm taking union of this set with A. So that is one. And on the other side, what do? I take union of A and B first, and then I take union of this set with C. So what this property tells us is these two are same. That means you can take union whichever you like first. So I can take A union B first or B union C also first. It won't make a difference. Okay. And same thing is going to work for intersection. That is A intersection B intersection C will be same as A intersection B intersection C. Okay. So union and the intersection, these two operations on sets, they satisfy the associative property. So I will give you all an idea of the proof of the first one, and you all can do the second one in a similar way. Okay, so let's see the proof. Yeah, so let's look at the proof. What I want to prove is A union B union C is same as A union B union C, the first one. So I will, how do I show that two sets are equal? I will have to take a point here and I have to show that it is that side, and I have to take a point that side and I'll have to show that it is this side. That's the standard way. Okay. So let X belongs to A union B union C. What do you mean by this? That means X is in this or in this. So this means X belongs to A or X belongs to B union C. Now what do you mean by saying X belongs to B union C? Again, the definition of union. That means X belongs to A or X belongs to B or X belongs to C. So finally what I'll do, I'll club these two conditions together. Okay, so X belongs to A or X belongs to B, I'll club them together. It means the same. I'm not changing the meaning, and I will leave this aside. X belongs to C. Okay. Now when I say X belongs to A or X belongs to B, this means X belongs to union of A and B, or it could be in C also. That means X belongs to union of these two A and B, or this. That means X lies in A union B union C. So what did we prove? We proved that A union B union C is a subset of A union B union C. Now in a similar way, you can start with a point here and you can show that it is this side, right? So that will show that these two sets are equal. Okay, the other side will go exactly in the similar way. Okay, so I expect you all to do that and hence conclude that these two are same. Okay, so the operation union of sets, it satisfies the associative property. Okay, now, and the second one, intersection, I expect you all to do. Okay, so please give a try for the intersection property as well. Okay, now look at this one. This says, supposing I have two sets B and C such that B is a subset of C, then I have to prove that for any set A, I can take union of A on both the sides, and that will give me A union B is a subset of A union C. Okay, so I can take union of any set here. If I know that B is a subset of C, I can take union of A on both the sides. Okay, and I can take intersection as well, and I'll have A intersection B is a subset of A intersection C. So I can intersect or I can take union of any set I like on both the sides if I have a relation of the form B is a subset of C. Alright, so again I will prove the first one and I'll leave the second one for you all as an exercise. Okay, so let's prove the first one. That says we are given that B is a subset of C, and we need to prove that A union B is a subset of A union C. Okay, so you have to keep one eye on what you need to prove. Okay, so I need to prove that A union B is a subset of A union C. So I'll start with a point in A union B. So let's do that. So let X belongs to A union B. That means X is either there in A or B by definition of union, right? So that is X belongs to A or X belongs to B. But we are given that B is a subset of C. That's the hypothesis. Now if X is there in B, then it will come in C also, because B is a subset of C. So I can write this further is, since B is a subset of C, whenever the point X comes in B, that point will come in C also, right? So from the second step here, what I can conclude, X belongs to A or X belongs to C. It's as good as saying this. And if X belongs to A or X belongs to C, then where will X lie? In the union of these two sets, A and C. That means X belongs to A union C, correct? And that's what we had to prove. So we started with a point in A union B, and we showed that it is there in A union C, thus proving statement 1. Okay, so I expect you all to do the second one in a similar manner. Okay, now one more problem here. This says if A is a subset of C and B is a subset of C, then union of A and B will be a subset of C. Okay, to understand this better, what you can do is you can just draw a picture. Supposing I have a set C here, this is my set C, and what we are given is A is a subset of C and B is also a subset of C. So let's say A is here, that's A, and supposing I have the set B here, let's say this is B. If A is a subset of B and B is a subset of C, then you can clearly see from the diagram that when I take union of A and B, that is when I take this shaded region which I'm shading right now. Okay, you need to shade it properly. I'll just scribble and I'll leave it. Union of these two sets A and B is also lying inside C. That means it's a subset of C. So if you have two sets which are subsets of the same set, then the union of these two sets will also be a subset of that set. Okay, so if A is a subset of C and B is a subset of C, then A union B is going to be a subset of C. And a similar result you have for intersection as well. Not similar in the sense analogous, not same. Okay, not exactly the same. This says if A is a subset of B and A is a subset of C also, that means A is a subset of two different sets B and C. Then we have to show that A will be a subset of the intersection as well. Okay, so in a similar way you can draw the diagram and you can visualize this, the second one. I will prove the first one and I will leave the second one for you. Okay, so let's go on to prove the first one. We are given that A is a subset of C, B is a subset of C. We need to prove that A union B is a subset of C. So let's start with the point in A union B. So let X belongs to A union B. We have to show that X is there in C. Okay, now X is there in A union B, that means X is there in A or X is there in B. So you have either this statement or this statement, but A is a subset of C, that's given to us, and B is also a subset of C, right? So in either case X will end up in C. If X is in A, then it is already in C because A is a subset of C, and if X is there in B, it is already in C. So in either case X is in C. So this implies X belongs to C, and hence A union B will be a subset of C. Okay, and similarly you can do the other one also. I'll just do it, I'll quickly rush through it. So I'll start with the point X in A. Okay, so A is a subset of B and A is a subset of C, that's given to us. That means X is there in B and C as well, and that means X is there in both of them, B and C. That means X is there in the intersection, and hence A is a subset of B intersection C. Okay, so these are two trivial results which we will be using some way or the other. Okay, Next, distributive property. Okay, the way we have distributive of multiplication of real numbers over addition, in a similar fashion we have distributive property of distribution of intersection over union and distribution of union over the intersection. So if I have three sets A, B and C, then A intersection union of two sets B in union C is same as A intersection B union A intersection C. Okay, so these two mean the same. That means you can distribute this intersection over the union, and you can do that for union as well. A union B intersection C is same as A union B intersection A union C. So if you draw the Venn diagrams for this, it's very easy to understand why these two are equal, and it's very you get a clear picture what is happening. Okay, so I want you all to draw the Venn diagrams for both these and verify using Venn diagrams that these two are actually true statements. Okay, so I will prove the first one again and I'll leave the second one for you all. So let's go on to prove the first one. So I have to show that two sets are equal. So we show that they are subsets of each other the standard way. Okay, so let X belongs to the first side, A intersection B union C. So I'll take a point X in A intersection B union C. That means X is there in A and it is there in B union C as well, because I'm having intersection in between. So this implies X is there in A and X is there in B union C. Now X is there in B union C, what you can say from this? X is either there in B or X is there in C. So you can split it up this way. So finally I have X is there in A and X is there in one of B and C. Now there are two possible cases here. X is definitely in A. So the first case is X is there in A and here X is there in B. Or X is there in A and X is there in C. These are the two possibilities. So this implies X is there in A and X is there in B, or X is there in A and X is there in C. Now if X is there in A and X is there in B, that means X is there in the intersection. So X is there in A intersection B, or X is there in intersection of A and C. Right? So X is there in this or X is there in this. That means X is there in union of either this set or this set. It's in the union of them because it's there in at least one of them. So that means X is there in A intersection B union A intersection C. So if you start with any point in the set on your left hand side here, you can show that it is there in the set on the right hand side. Right? So left hand side is a subset of the right hand side. Now we need to prove the opposite. A intersection B union A intersection C is a subset of A intersection B union C. Again, you can do it in the standard way by taking a point here and showing that it is this side, but I'll use a different way. Okay. Now we know that B is always a subset of B union C and C is always a subset of B union C, right? A basic result in the set theory that you all have learned in the lower classes. Now I will intersect A on both the sides. Okay. In one of the properties just now we saw that if I have B is a subset of C, then I can intersect any set I like on both the sides. So that's what I'll do here. So I'll intersect A on both the sides. Okay. So intersecting A on both the sides we get. So here I'll get A intersection B is a subset of A intersection B union C. And that's what I have here. And along with this, I will intersect A here also in the second expression. So I'll have A intersection C is a subset of A intersection B union C. Right? So I have this. Now, this A intersection B is a subset of this set, and A intersection C is also a subset of the same set. That means I have two sets which are subsets of the same set. And again, in the one of the previous slides, I have done a result, right? So by using one of the properties which I put on the last slide, the union of these two sets will also be a subset of that set, right? So A intersection B union A intersection B. So union of this one and this one is a subset of this common set A intersection B union C. And that's what we had to prove. So we have proved that both of them are subsets of each other, and hence these sets are equal. Okay. So I expect you all to do the second one, that is distributivity of union over the intersection. Okay. I hope it will be possible. Now, in the previous slides, we saw union of two sets and intersection of two sets. What if we have finitely many sets with us and I want to take their union and intersection? Okay. So this is called operation on finite number of sets. So supposing I have n sets with me, finite number a1, a2 up till an. Okay, so these are some arbitrary n sets with me. Then the union of all of them, union of ai for all I running from 1 to n. So union of all these is this set. Okay, its idea is the same as you do it for two sets. So which points will come in the union? All those points, which one of them, right? So union of all these ai's, a1, a2, a3, this expression I can I can write it as this: a1 union, a2 union, and I can keep on, that's union, the last one an. So this is the short form for this. Okay, union of I running from 1 to n, and that is collection of all the points x such that there is at least one suffix k from 1 to n, such that x will come in that ak. That means x should come in at least one of the AKs, where k is running from 1 to n. Then only the point x will come in union of all of them. Okay, so that is x will come in the union ai's if and only if x is there in AK for some k from 1 to n. So there should be at least one AK in which x is coming, then it is going to come in their union. Okay, so this is the meaning of union of finite sets. If I have finitely many, then also I can define the union in this manner. All right. Next is intersection. In a similar way, if I have sets a1, a2 up till an with me, finite number of sets, then I can take intersection of all of them. Okay, and that is, if you want a simpler expression, you can write it this way: a1 intersection, a2 intersection, and so on up till the last one. Okay, that is same as this. Okay, so that's a short form to write this expression. Intersection of all the ai's, I running from 1 to n. It is, when will a point come in intersection of all of them? When that point is there in each and every set a1, a2 up till an. So this is collection of all the elements x such that whenever you take a suffix from this set 1, 2 up till n, for every k in this suffix, for every k in this set 1, 2 up till k, it's three dots here. For every k in this, that x has to come in that ak. That means x is there in a1, it is there in a2, it is there in a3, and it is there in an as well. Okay. So in another way, I can write this as x belongs to intersection of all the ai's I running from 1 to n, if and only if this, so x will come in this set if and only if x is there in ai for every I from 1 to k. So x is there in ak for each k from 1 to n. Okay. So this is how you define intersection of finitely many sets. All right. So I'll wind up with this session here, and we will continue with this subtopic in the next video. All right. These are my references. Thank you.